The reason I put a tree on the title slide is because what I want to focus on is the ways in which reconstructing evolutionary histories, family trees, so to speak, of living organisms is a predictive tool. Okay, now, when people think of one of the great hallmarks of science, of course, is its predictability. We can make predictions based on scientific principles. But if you think about evolution, this is something that happened in the past. So you might think this is not something you would predict because it's already happened. But in fact, evolution is as predictive as any other kind of science. Now, last year we celebrated the bicentennial of Charles Darwin's birth. Last year was actually a big deal for a lot of big anniversaries. It was also the 150th anniversary of the origin of species, the 100th anniversary of the discovery of the Burgess shale fauna, and the 50th anniversary of the discovery of Zinjanthropus. I mean, it was this big sort of massive anniversary fest that we had last year. Darwin didn't invent the theory of evolution by any means. People at that time in the 1850s were already talking about descent with modification. He came up with what we now believe to be the primary mechanism that drives evolution, natural selection. It wasn't really accepted that widely in his time, but eventually it did predominate. But it was because of him that we can now actually draw conclusions about the past. Now again, one of the things that we like to hype about science is we can make predictions. We can predict solar eclipses many centuries into the future. We can take a small robotic small machine and using simple Newtonian mechanics, maybe a few little corrections from Einstein, send it all the way to a moon orbiting Neptune and get good pictures of it. I mean, we can be that precise. Predictability is one of the things that really sets, I think, science apart from many other fields of human endeavor. And yet, how will we use the past to draw predictions? That's what I want to focus on today. I want to talk about how evolutionary histories, first of all, it'll help us illuminate the past, but also how we can use them in our daily lives. Okay, this is something that actually has practical benefit. And this goes back to things that people have been noticing. This is a little bit cut off there at the end. That frog actually does have a head. This actually goes back to even before Darwin. Linnaeus, Carolus Linnaeus was one of the first to really discuss how living things seem to form internested groups. So I can take 4 randomly selected vertebrates here, and what I would notice is that these two share similarities with each other that they don't share with the others. And so they sort of form a group of their own. But the lizard also shares things with the chimp and the cat that none of these 3 shares with the frog, and that the frog also shares things with the mammals and the lizard that none of these would share with maybe a fish. Okay, this forms a hierarchy, a set of groups nested within groups. Okay, now this is an obvious pattern. Human beings can't have failed to have observed this. What Darwin did that was revolutionary was really free us to interpret these as what they are, the products of descent with modification. It's this evolutionary history that generates these groups within groups, these hierarchical sets. And these are wonderfully predictive. I'm going to give you, first of all, how do we build these phylogenetic trees? That's what we call them. A phylogeny is the evolutionary history of a group of organisms. How do we build these family trees? I'm not going to go through the methods, but the sources of information we have are legion. We can get it from molecular data. This is very common these days. We can get information from the actual genes of an organism and from its relatives, and we can compare the DNA of different species, make some assumptions about processes of evolution, and then actually come up with a set of relationships. We can also get this information from the animals themselves, from their anatomy, their morphology. Now, a lot of people will tell you that molecular and morphological data are at odds. That's actually not always the case. Usually they give you fairly similar results. There may be a few conflicts out there, but for the most part they give you fairly similar results, and we can use both to reconstruct these evolutionary histories. Now, what do I mean by these being predictive? Let me give you an example of how these can be predictive about the past. This is a tortoise. If you've ever seen a tortoise yawn, I don't know if anyone here has ever been bitten by one. I haven't, but I've seen them yawn. They don't have any teeth. Okay, just to prove that to you, here's the skull of one, and as you can see, it's edentulous, has no teeth. Okay, tortoises, turtles never have teeth, at least in the modern world. Now, until recently, the only evidence we had for teeth in turtles was a fossil called Progonachilles from Germany, which had teeth on the roof of the mouth. It had teeth on the palate, but it didn't have teeth on the margin like most other vertebrates have. Well, let's put turtles in an evolutionary context. Here's a family tree that shows how turtles are related to crocodiles, dinosaurs, which include birds. Birds of today don't have teeth, but their ancestors obviously did. Lizards and snakes, and then mammals down here. There is some controversy as to exactly how turtles are related to other groups of reptiles. I'm just expressing that by drawing it this way. But this family tree is pretty stable as I've drawn it. What we know is that dinosaurs, crocs, lizards, mammals, for the most part, do have teeth. Okay? What we would assume is that these teeth were present in their last common ancestor. We don't necessarily know that for sure, but we would assume that because it's easier to assume that than to assume that each of these lineages independently evolved teeth. That's just a simpler assumption, and for the most part, this holds out. So we assume that teeth were present in this common ancestor, and that this feature was then passed on to all of this ancestor's descendants. Okay? Now, what that means, logically, is that turtles, which have no teeth, have ancestors that did. That's a natural consequence of this pattern. All we know is that somewhere along this lineage, teeth were lost. Now, this actually gives us a prediction. We can predict that we should find, if not a turtle with teeth, then something that is more closely related to turtles than to anything else with teeth, because turtles with no teeth are descended from animals that did. Pretty simple. A couple of years ago, Odontochelys, where the name was clipped off, Odontochelys was discovered. Odontochelys, the name means toothed turtle. It's from China. It doesn't have a complete carapace. It doesn't have a complete shell on the back, but it does have most of the plastron, most of the shell on the bottom. But it also has dentition right around the margin. It has full teeth. So we've actually now got a turtle with teeth, which is exactly what we predicted would be found. It was also found in rocks of approximately the age we would have expected. It's a little bit older than Progonachilles. So we fulfilled these predictions with these fossils. And the examples of this are legion. Another quick example, a dolphin, whales, dolphins, don't have hind limbs. If you look at the skeleton, they've got a little bit of a remnant of their pelvis, maybe a remnant of the femur, but no actual hind limb. And yet, they're mammals. Okay, the females give milk to their young, they breathe air, they're warm-blooded. We would expect that these would have had ancestors with hind limbs, since mammals ancestrally had hind limbs, and now we've got whales with legs. We predicted they would be discovered, and they've been discovered. So we can make predictions about future discoveries using this. But it's not just future discoveries of the ancient past, it's also something we can use for our own benefit. Let me give you an example. This is a brown snake, Stereria decay. This is something that you might find here in Iowa. They're common. They get to be about a foot long. They like to eat slugs, earthworms, maybe little toads if they can catch them. They're colubrids, natricine colubrids. They're related to garter snakes, completely harmless, okay, absolutely harmless. This is also a brown snake, the western brown snake, Pseudonaga nucalis. This is an Australian species. It's an elapid. They get to be about 5 feet long, maybe 6 feet long. They eat small mammals and lizards. They are related to cobras and taipans. They're elapids. They're deadly venomous. Now, first of all, people will sometimes say that taxonomy is just stamp collecting. It's just semantics. Who cares? I submit that knowing the difference between one kind of brown snake and the other can be somewhat more than just semantic, especially if you're asked to handle one. The reason I'm showing you this picture, and by the way, there was a pretty thick piece of glass between me and the animal when I took the picture. I didn't just kneel down, But And it has to do with what it means to be a brown snake in Australia. There are several different snakes in Australia that are called brown snakes. And they're called that for very obvious reasons. They are snakes, and they're brown. Hence, brown snake. They're all extremely, extremely venomous. The thing is, snake venom evolves, just like any other part of an organism. And what that means is that if you get bitten by one snake, that venom is likely to be more similar to a closely related snake than to something more distantly related. Which, if you think about it, means that if you get bitten by one kind of snake, you can predict what kind of antivenom you might need. And that's important because brown snakes don't describe what we call a monophyletic group. They don't describe a natural group. These two brown snakes here are in fact related to each other, but the king brown snake is actually more closely related to this one, which doesn't look at all like a brown snake. It's kind of a black and red snake. And so if you get bit by a king brown snake and they give you a western brown snake antivenom, you'll die. If you get bitten by a king brown snake and get red-bellied black snake, that might work. So you can actually predict, and this is useful because there are several snakes here for whom no one has ever collected venom, at least not voluntarily. And no one has ever, and no one's actually tried to see how it would react to human tissue and what kind of antivenom to use. But we can actually use this predictively. If we got, this one here called the bardak, we don't know exactly what its venom is like, but it's probably going to be a lot like the death adder, since that's its close relative. And so this is something we can use predictively. This is also useful in epidemiology, which I didn't have a chance to put in any examples from the swine flu epidemic or whatever that's been going through, but just a quick example. Viruses and bacteria and other pathogens also evolve. And a lot of the characteristics that go along with them themselves evolve and are related to their ancestry. So for example, if you look at, suppose I've got some sort of virus that I find and people are getting sick from it, I want to control it. If it's in this group here, if it's related to West Nile or dengue fever, trying to control ticks isn't going to do anything. Even if I've never actually found a mosquito carrying this virus, I would predict that it's going to be a mosquito-borne virus, and if I want to start controlling their populations, I'm going to start draining ponds. I'm not going to worry about spraying fields that might have ticks, at least not right away. If I find evidence that I was wrong, okay, then take care of that. But we can actually start acting before we actually know that much about the virus itself because of its relationships.